Well, good afternoon, everyone. My name is Patrick. I'm a postdoc in Silke's group in Nottingham, and I'll be chairing the session where we are going to hear from David Horváth from King's College London, where David is now working as a postdoc, and he's going to report on his research on inhomogeneous quantum quenches in the sine-Gordon theory. So David, thank you, and the floor is yours.
Okay, thank you very much. Good afternoon, everyone, and so thanks for the opportunity to talk here. So now this afternoon I'm going to talk about, in fact, this work about inhomogeneous quantum quenches in the sine-Gordon theory, which was done in collaboration with Spyros Sotiriadis, Márton Kormos, and Gábor Takács. So based on the title, you can readily guess that I will be talking about 1D physics. It's a one-dimensional model, and some integrability is involved also in the game. But apart from talking about a really physical situation, I would also like to devote some time to a very non-trivial method. I would like to advertise this method by which the quantum simulation of this problem was made possible. But jumping back to physics, and before giving you a proper outline, just for those who are experts in the in this field of physics, in this non-equilibrium physics, it's very easy to summarize what I will be talking about in few lines. Namely, I will consider I will consider an inhomogeneous quantum quench in the sine-Gordon model. Of course, I will define everything later on. So we'll consider a particular inhomogeneous Hamiltonian. Here you can see an inhomogeneous term, which is added to the homogeneous sine-Gordon model. And this term consists of the spatial derivative of the fundamental field, which is proportional to the topological charge density. It's multiplied by a classical external and space-dependent field. And first, we will take a look at the ground state of this inhomogeneous Hamiltonian. It turns out that this ground state has interesting properties. And then we perform a quantum quench consisting of switching off this inhomogeneity. And we will be looking at the time evolution from this inhomogeneous initial state. It's governed by the homogeneous Hamiltonian, and in particular, we focus on the time evolution of this dx phi, so the topological charge density. But now to give you a really proper plan for today. So it goes as follows. After some motivating words, I will introduce the sine-Gordon model to you, both the quantum and the classical models. So also the classical, and not only for pedagogical reasons, but I will make important comparisons between the quantum and the classical models. And after the introduction of the model, I will talk about physics, which is split into two parts. First, this inhomogeneous ground state will be targeted. And in particular, one can observe an interesting transition phenomenon in this inhomogeneous ground state, and this is what I will explain to you, the origins for this transition. And interestingly, this, or perhaps not so interestingly, but this transition in the ground state then also inherited into the features of the time-evolving quantities. Nevertheless, when one studies time-evolved quantities, this transition has a different nature. And I will comment on that and also give not necessarily an explanation, but I would say an interpretation for that. And once the physics is over, I mean, this problem is really discussed, then I would like to talk about some methods, or more particular, in particular one method, which is called TCSA. It's the acronym stands for truncated conformal space approach. This is the method it's a numerical method which made us possible to perform our simulations, and I would like to just summarize the essence of this method. And finally, I will summarize, and I will give, I think, quite some extended outlook. I will mention another very similar inhomogeneous case with very non-trivial findings. And then I will say a few words about the experiments of the Vienna group, where sine-Gordon experiments exist. In particular, I would like to say a few words about the very recent advances this group, the group has managed to install. And to finish my talk, I will also say a few words about other potential applications of this TCSA method. So that's the plan. And first, some motivating words. I think it is there is no big need or real need to convince you why inhomogeneities are interesting. I could have listed many more things. One thing that just randomly came to my mind is that besides the fact that inhomogeneities are say always there in real world systems, or sometimes they are really associated with remarkable phenomena. So sometimes they are also quite crucial. If you think of nucleation phenomena, or for the quantum Hall effect, where we know that the presence of impurities is in fact quite important. And now if we go to 1D and 1D physics, and the questions around inhomogeneous cases and inhomogeneous time evolution, because it's an interesting problem and it has attracted lots of attention. In fact, and in particular in integrable models, quite powerful methods have already been developed to deal with inhomogeneous problems. So there are two main types of these methods. There are perturbative approaches, and there are hydrodynamics-based methods or methods which are of some hydrodynamic nature. So these methods can work very well under certain circumstances. Nevertheless, you can always come up with physical situations where the underlying assumption of these methods do not work. And in this talk, I would like to give you such an example, I think an interesting and relevant example, where you cannot really treat the problem with a hydrodynamic approach, neither perturbatively. So in that case, what you really need to do is to solve the full quantum dynamics, at least up to intermediate or short times. Yes, and another motivation, and this is in particular for the sine-Gordon model, is that, as I already said to you, this model exists, or it is claimed to exist in real-world experiments, in particular in the experimental lab of Jörg Schmidmeier in Vienna. So I will talk about this experiment a bit later, I mean, in the Outlook section of my talk, where I will try to introduce this experiment. And here I would merely mention that very recently 2 other proposals have been popped up, how this sine-Gordon model could be realized. So apparently there is an interest among researchers to realize this very nice model. And one proposal says that the model could be realized in terms of circuits of Josephson junctions, so superconducting junctions. And there is another proposal which claims that Bose-Hubbard ladders can do us the job. These are all very non-trivial proposals, and they are proposals, so they have not yet been realized. To the best of my knowledge, this latter proposal, it's I think Immanuel Bloch is involved, and as far as I know, they are proceeding. So probably this will be realized soon. So this is for appetizer, and now I would like to introduce the sine-Gordon model for you. And as I said, first we start with the classical case. It's a bit more pedagogical. So here you can see the action of this classical field theory. Phi is our fundamental field. We have this famous cosine potential, and beta, which appears here, can be regarded as an interaction parameter. From the action, of course, you can derive the equation of motion, which involves this sine term, and that's the explanation for the name. It is well known that the solution of this equation of motion, or the solutions, are quite interesting and quite unique. You can have solutions like this soliton solution, which is a so-called topological excitation. You can observe that this solution is such that it interpolates between 2 neighboring vacua of the cosine potential, and you can have an anti-soliton which does the same thing, just sort of in the other direction. So these solutions are topological because of this interpolating nature, but you can have other solutions of this equation of motions, topologically neutral ones, and these are the breeder configurations. And of course, the model is integrable, so you can have a multi-soliton, anti-soliton, multi-breeder solution, and you can boost everything so they can move. Crucially, because of integrability, they keep their shape after scattering events. So here, an important concept I said many times is the topology on the topological charge density. So the topological charge density is in fact an important quantity for this talk. And you can see that it is defined as follows. So it's essentially the spatial derivative of the field multiplied by this beta over 2 pi. And its interpretation is quite natural. if you integrate this quantity over a spatial region, this quantity tells you the number of solitons minus antisolitons. So the soliton carries a topological charge 1, the antisoliton carries a topological charge -1, and as I said, the breeders are neutral configurations. So this is what you have to know about the classical theory, and an interesting thing. So now we go quantum, is that but in the classical theory, this beta parameter is quite innocent. And now if we go quantum, you can see that in the quantum regime, it becomes very important, because based on the value of this beta parameter, your theory behaves different ways. So first of all, you can distinguish 3 different regimes of your quantum model, depending on the value of the beta. You can have the attractive regime, you can have the repulsive regime. The name comes from the fact that in these regimes, the soliton and the antisoliton attract and repel each other. There is a free fermion point as well, for which I will give, it's a specific point, and I will give an explanation or insight why it's there on the next slide. And crucially, beta cannot be arbitrarily large. If it's beta squared is larger than 4 pi, then there's the BKT transition, and it's not longer a sine-Gordon model, what we are talking about. The spectrum of the model is the following. The solitons, the solitonic excitations are always there, irrespective of what regime we are. But the breeder excitations, they exist only in the attractive regime of the model. Their mass is quantized, it's quantum theory. But also the number of different breeder species depend on this interaction strength, this beta parameter. So that's what you have to know about the spectrum, the particle spectrum, the particle content of this theory. It's still an integrable theory. There is one technical remark. It's not so important, but it's worth stressing that. So in this work, I will consider only the attractive regime and the free fermion point. And if you want to make comparisons between the quantum and the classical theory, a reasonable way to do that is to equate the lightest breeder mass on the side of the quantum theory. And in the classical theory, you have a mass scale, which you can just put into the coupling in front of the cosine. So equating these 2 quantities, you can make reasonable comparisons. But it is technical, and coming back to physics, I would like to sort of unveil this strange free fermion point. How is it possible that it's there? And the explanation for that is not at all intuitive. It's based on a very famous and actually well-known duality between the sine-Gordon model, which is a bosonic quantum field theory, and the other theory, on the other side of the duality, there is the massive Thirring model, which is a fermionic quantum field theory. And it is well known that solitons on one side corresponds to fermion on the other side. And on the side of the Thirring theory, you can see that at this specific value of beta, the interaction term vanishes and the theory becomes just a theory of Dirac fermions. So in other words, the free Dirac theory is incorporated in the parameter range of the sine-Gordon model. It's quite a nice thing. But there is another free theory, which is there in the parameter regime, the parameter range of the model, namely the Klein-Gordon model. It's much, I think it's much more obvious. If you send beta to 0, you can just actually essentially expand the cosine potential, and you will see immediately that you end up with the Klein-Gordon theory. So both free theories, natural free theories, are there in the sine-Gordon parameter regime. And the Klein-Gordon theory, of course, is there as well in the classical theory. So it's not specific to the quantum case. So this is in general about the sine-Gordon model, and now I have to specify a bit more the inhomogeneity, the initial inhomogeneity, what we exactly consider. So I said to you that this is the inhomogeneous term. I also said that dxi is just proportional to the topological charge density. So first of all, the interpretation of this term is, it's not written down, but this J prime, for reasons of convenience, we denote it as a derivative field. So it's an external space-dependent field, but you can merely regard it as a chemical potential because it's coupled to the topological charge density. It's a chemical potential for the topological charge or for the soliton and antisoliton excitations. Because of the method with which we can tackle this problem, we will be in finite volume and we will impose periodic boundary conditions. So actually, this is the Hamiltonian I will really be considering. But I think it's more important to say a few words about this external chemical potential, J prime, because we chose a very particular potential, which is written out here and visualized by this plot. So this J prime it's a simple Gaussian. It's a simple Gaussian. Its amplitude is denoted by A. It's an important control parameter in the model, so that's why it is marked by red. We can play with the height of this Gaussian. And this Gaussian also has an offset value. And the offset value is chosen in such a way that the total integral of this external field is 0. We did this choice for the following reasons. You can show that even with this inhomogeneity, the topological charge is a conserved quantity. And if you impose this neutrality condition, you can ensure that your system is, the ground state of your inhomogeneous system is in the topologically neutral sector, which is, for many reasons, is the most natural or the most convenient to look at. So this will be this is the inhomogeneous chemical potential, and it's crucial that we will be able to tune the amplitude of this Gaussian. And there is a very funny fact about this initial inhomogeneity, and in particular about the classical version of the inhomogeneous problem. So first of all, I will call the lowest. Yeah, first of all, you can regard this problem also classically. You can write down the classical Hamiltonian. You can define the same inhomogeneous term, and it makes sense to talk about the lowest energy configuration, which I will merely call in a bit sloppy way a classical ground state. And this classical ground state can be determined by a differential equation, more precisely a boundary value problem. And if you take a look at this differential equation by a simple rescaling of your field, you will immediately see that classically, only this combination of the parameters that matters for the physics. So remember that A is the amplitude of the external disturbance, the chemical potential, as B is the interaction parameter, and there is a complete interchangeability between these two parameters in the classical theory. Such an interchangeability cannot be true in the quantum case, if not for other reasons, because I said to you that beta is bounded from above. But I anticipate that in the attractive regime, more precisely in the explored range of parameter, this interchangeability qualitatively will also hold in the quantum regime of the model. So this is the introduction, and now let me move on to discussing the ground state first of this inhomogeneous Hamiltonian. So let's look at the ground state. And we study the ground state by looking at these field profiles. So this is the canonical field, and this is the topological charge density. So essentially, it's spatial derivative. And the interesting thing which is going on is perhaps better visualized by this left plot. So what we can see here is that, first of all, the interaction parameter is kept fixed, and the amplitude of this Gaussian is increased gradually in a more or less equidistant way. And what we can observe is a sharp transition in these profiles. This is the most important observation, but we can make some other observations as well, namely that below this transition, the quantum and the classical profiles, the quantums are shown by dashed line and the classical ones by continuous lines, they are very close to each other. Above the transition, they also have similarities, but there are also some differences, namely that the classical profiles develop extended plateaus, but these plateaus are absent in the quantum case. So these are our observations in this case. And of course, we can play the same game in the other way around. Namely, we can fix the chemical potential and change the interaction parameter. And as I said to you, it's a trivial thing in the classical theory, but it's non-trivial in the quantum. Nevertheless, from the viewpoint of the existence of these transitions, we can still see that also in the quantum case, it behaves in a similar way. So you can, if you wish, you can interchange the role of these parameters. You can make some other interesting observations, namely that there is not only one transition, but actually more than one transitions. And taking a look at the y-axis, you can also notice that the distance between these two plateaus in the classical case is 2 pi. So natural explanation is that this transition has something to do with the soliton content of the initial state, and in fact that's the explanation. And to make it a bit more concrete, in this next slide I show you 3 cartoons. They are pendulum chain, and the thing to note about pendulum chain is they are actually nothing else but the discretized version of the classical sine-Gordon theory. So we can imagine, or one can imagine, that if we have a tiny local disturbance, a Gaussian chemical potential here, then the pendulum chain will respond in a way. Nothing drastic is expected to happen. But if the amplitude of the Gaussian is big, then because our cosine the potential is bounded, energy for the system, it can be energetically more favorable if it introduces a twist and an anti-twist, a winding and an anti-winding, and this way it can ensure that over a spatially extended regime, the system is really in the minimum of the cosine potential. And of course, a winding and an anti-winding corresponds to topological excitations, namely soliton or anti-soliton excitations. And in fact, you can, further increasing the amplitude of your external chemical potential, you can have more of these windings as well. What I would like to emphasize here is that you can show explicitly that the transition I was talking about is completely discontinuous in the classical theory. It's like a bifurcation. It is not expected to be discontinuous in the quantum case. We have no clear evidence for that, but it's very unintuitive. Nevertheless, as I said, it's still a very sharp transition from this, so no soliton and the soliton and an anti-soliton case. And one more funny thing, which is, I think, worth mentioning, is that if you take a look at this plot, you can see it's the classical profile, but far away from the Gaussian. So here is the Gaussian disturbance. And here what you can see is that all the profiles corresponding to different A times beta, they collapse on the same curve. And this curve is a perfect anti-soliton. So what you have here in this region, you get a perfect anti-soliton in the classical theory. Here in the middle, it's not a perfect soliton. It's a topological excitation. It's close to a soliton, but not a perfect one because the Gaussian slightly distorts it. But anyhow, what is happening is actually an injection of a soliton and an anti-soliton, at least classically. So now we can take a look at again the quantum theory and understand some important differences between the quantum and the classical case. So in the classical case, we have a perfect and localized anti-soliton and the localized, I would say, imperfect soliton. In the quantum case, on the other hand, what we can claim based on the shape of these figures, that here in the middle, what we have is still more or less a localized soliton. But in the quantum case, the anti-soliton, which must be there because of the neutrality condition, in fact, is not localized. And the reason for that is here I again visualize the chemical potential. So here we have the soliton which is dragged, but apart from this region, the chemical potential is completely featureless. In other words, there is nothing that would make the anti-soliton localized. And because it's a quantum theory, we expect that by default, then it then must be delocalized. And because it is delocalized, this is exactly the explanation why we do not see this nice extended plateau in the quantum case, only in the classical case. So as you can see, based on these essentially semi-classical considerations, we could fairly understand what is going on in this ground state. And essentially, the keyword is that with this external inhomogeneity, we could inject solitons and anti-solitons in the system. So that's about the ground state. And now we move on. I will skip this this slide, and now we move on to the time evolution. So what happens when we switch off the initial inhomogeneity and do the time evolution with the homogeneous Hamiltonian? We will focus on, in particular, the time evolution of the topological charge density. Let's see what happens in this case. So here I'll show you density plots of the density. So the density here is the topological charge density. The horizontal axis is the spatial direction, The vertical one is the temporal direction, and here we also have a color code. Again, we can make several observations. One observation is that, yeah, from the initial bump, from the middle, we have the light cone. Okay, that's very nice. But what we can observe is that there seems to be again a transition or a smooth crossover compared, I mean, if we take a look at the different ends of this plot. Of course, it is not surprising in the sense that if we know that there is a transition in the initial state, then it is in fact expected that this transition must be inherited, and also time-evolved quantities should show it. But what is, I think, interesting is the nature of this transition, because what you can see is an interpolation from a dynamics which is like the dynamics in the free fermion case. These are exact free fermion simulations, numerically exact. And on the other end, you see Klein-Gordon dynamics. These are again exact Klein-Gordon simulations. So there seems to be a crossover from a dominantly fermion-like to a Klein-Gordon-like behavior, at least in this topological charge density, a fermion-boson-like transition. The transition is there in the classical case as well. But of course, this fermionic feature, it exists only in the quantum theory. So you can really see that this is a quantum effect. The classical theory shows very rich structures, but it's certainly different from the quantum case. So we can also convince ourselves that what we do in the quantum model is really quantum. It's not semi-classical. And again, this interchangeability of the parameters of the two important control parameters, beta and A, it's again there, at least from the viewpoint of this transition. In the quantum model, which is a not entirely trivial statement. But in this plot, there is something more which I would like to focus on. Again, this lowest, this bottom row, show exact free fermion dynamics. And what you can see is that, so the free fermion, the Dirac theory itself can show a transition, which I used to call boson-fermion transition, but it's there in the fermionic theory as well. So yeah, maybe the name is not entirely accurate. Perhaps it's a Klein-Gordon. Yeah, okay. And anyway, so the transition is there also at the free fermion point, so in the free fermion theory. And this fact is perhaps not surprising, but on the next slide, I would like to say something which is perhaps a bit more surprising. And first of all, I would like to give an interpretation of this boson-fermion transition. And the way I like to think of this transition is based on the distinction of inherent and collective degrees of freedom of a theory. It is quite well known and well established for the case of the sine-Gordon model. Actually, it's exactly due to the duality with the Thirring model that the solitons in the sine-Gordon theory corresponds to fermions or fermionic excitations, whereas the breeders corresponds to bosons or bosonic excitations. So these are the excitations or degrees of freedom which I call inherent. They are there in the theory. More precisely, they are not always there, namely that we know that if we approach the free fermion point from the repulsive regimes, then the breeders vanish. We lose the inherent bosonic degrees of freedom, which is also indicated by this wave function renormalization constant. So we only end up with fermions. And clearly, if we focus on the free fermion point, then we have only fermions. Nevertheless, we can still observe a bosonic behavior. And again, as I said to you, it's not surprising in the sense that everyone knows the keyword of bosonization. So, but the surprise is the following. So first of all, the explanation is that we can observe bosonic behavior because a fermion and an antifermion forms a quasi-bound state. This is due to the initial inhomogeneity, but still, because of this initial inhomogeneity, it's a collective degree of freedom. To make this statement a bit more precise, here I show you, yes, again, the topological charge density at a fixed point, namely x equals 0 as time passes, and these are the exact Klein-Gordon and free fermion curves. So you can very easily see the oscillation frequencies in the free fermion case that they correspond to twice the fermion mass. So you can convince yourself that in fact it must be a 2-fermion, it's a fermion anti-fermion state. You can also observe that the oscillations are damped, also in the Klein-Gordon case, but you can actually make this statement numerically accurate that the damping is larger in the free fermion case. It also confirms the fact that you can really think of these collective excitation as something not stable, but nevertheless it's there. It's relatively long-lived. At least it seems to influence the physics on short and intermediate timescales. So what can be interesting in the future is to go to the repulsive range, a repulsive regime of the model, where what you expect is that because of the repelling force between the soliton and the antisoliton, probably such an excitation, a collective excitation, is even more, its lifetime is even shorter. And what one may infer from this picture is that if you have a smooth and not too high amplitude disturbances in such a model, like the sine-Gordon theory, at least the short and intermediate time physics might be governed by such collective bosonic excitations. And actually we didn't do that, but estimating the lifetime is something that certainly in the free fermion point, it can be doable as well. But actually this is the end of my talk regarding the physics. So this is all I wanted to say about the inhomogeneous quenches in the sine-Gordon model. And now I would like to switch topic and advertise the main method, which was really the cornerstone of this whole work. Of course, many methods were involved in this project, but the crucial thing is, of course, the quantum evolution or the quantum inhomogeneous initial state. And to carry out the simulations, it was this truncated conformal space approach which was heavily used. So I would like to introduce this method to you now very briefly. So the main idea of this method is that quite generally, you can usually consider a quantum field theory, the well-defined quantum field theory, as a perturbation, as a relevant perturbation of a UV fixed point, so a conformal field theory. And in fact, you can use the Hilbert space of this UV conformal field theory for your quantum field theory. The main idea of TCSA is the following: is that we will regard our theory as a perturbation of a CFT, and first we put our theory into finite volume. This way we end up with a discrete spectrum, and now comes two crucial things. One crucial thing is if we have a CFT basis, then at least in 1D, it is quite often possible to give exact expressions for these matrix elements. So let's imagine that you want to perturb a UV fixed point by your RG relevant operator. You can usually compute the matrix elements in the conformal Hilbert space. And the other crucial thing is the finite volume, because if your spectrum is discrete, then the indices of your matrices are of course discrete. So at this stage, you have infinite dimensional, but discretely many, so your matrices are not continuous in the indices. That's the point. So how you do this problem tractable, numerically tractable, is that you introduce a truncation in your Hilbert space. You say that, okay, I truncate some elements from my Hilbert space, and this way you simply end up with finite dimensional matrices. And once you have finite dimensional matrices, you can do numerically almost whatever you want. Of course, not everything. Entanglement is a good example, which at least the spatial entanglement is not really. You cannot really target, or it's very extremely difficult to target by these methods, but many quantities can be efficiently computed. And one advantage of the fact of choosing a conformal Hilbert space is that so you can see that you have this truncation. You have to have this truncation, but of course with this truncation you introduce errors. But if you have an underlying CFT somewhere, then you can quite naturally work out renormalization group inspired ideas, how this truncation affects your quantities. In particular, you can get some analytic predictions. I mean, how quantities should depend with respect to the cutoff. And quite often you are able to eliminate or at least mitigate the truncation effect. So this is a big advantage of using this conformal basis. I would skip this slide, which is technical, and it just about the sine-Gordon and the underlying CFT. And I would rather talk about this sort of improvement of this TCSA method, which was recently done by my collaborators. So yeah, we now have the basic idea. You have finite dimensional matrices, but you very quickly realize that as long as you have periodic boundary conditions, these matrices contain lots of redundant information. So if you store them in your memory, I mean, it's yeah, there are lots of redundancy. So what you do because of this redundancy, to avoid the redundancy, is the following. It turns out that it's sufficient for many purposes only to define the action of matrices on vectors, which doesn't require the explicit construction of the matrix. This way you can get rid of the redundancies. So the key thing is that if you only know how your, say, Hamiltonian acts on a vector, then you're already at a very good position because you can compute the spectrum of your theory, because Lanczos and other Krylov space algorithms require only the action of your matrix on a vector. You can do time evolution, also imaginary time evolution, because the Chebyshev-Bessel method again only requires the action of matrices on vectors. And yeah, constructing matrix elements is trivial. So with this trick, because you don't have to store explicitly matrices, you can actually square the size of your Hilbert space, which can be of order 10 million. And in fact, if you consider inhomogeneous problems where there's no translational invariance, you really have to take into account all the momentum, all the subspaces of your Hilbert space with different momenta. Then you need a big Hilbert space. So I would say that this improvement was quite inevitable for the inhomogeneous quenches in the sine-Gordon theory. So yeah, this is a new improvement of this method, and actually we also did a program package which can be downloaded from archive. All right, and now that I think as a brief introduction or advertisement for the method, it's enough. So now let me give a summary and as I said to you, an extended outlook about what I was talking. So regarding the physics and the physical phenomenon I demonstrated to you, we saw first of all we were considering a particular quench protocol, an inhomogeneous quench, and a particular inhomogeneous Hamiltonian, and we could observe a transition in the ground state, which we managed to understand by semi-classical reasonings. It is due to the enhanced soliton anti-soliton content, which is triggered by the external inhomogeneity. And when we looked at the dynamics after the quantum quench, we sort of had another perspective on this phenomenon, which was more in terms of bosonic and fermionic degrees of freedom of the theory. But I'd like to mention one interesting implication for experiments, namely this interchangeability of these parameters, which we also observed in the quantum theory. You have to know that the current experiments are at small beta, but this interchangeability is expected to hold in that regime in the quantum model. So if the experimentalists manage to fabricate a high enough chemical potential, then in principle, this phenomenon can be observed in experiments as well. And now some outlook, actually. First of all, I would like to show you a very similar inhomogeneous protocol to what I was discussing, but on a spin chain with very surprising results. So it's a simple spin chain, and the authors considered a global quench plus a local impurity, namely a single spin flip on top of a global quench. And the observation was that this single innocent impurity, a single spin flip, causes late time global effects at late times. It's a very non-intuitive finding. And of course, one can wonder about if anything similar can be observed in a quantum field theory. And the answer is actually more likely to be no, but we are not yet sure about it. Nevertheless, if it can be observed, anything similar can be observed in the quantum theory, then the sine-Gordon model and a similar protocol that I was discussing can be a good candidate, because not just because of the similarities. I mean that we had a global quench because of the offset of the, if you wish, of the chemical potential, and then a peak, so an impurity. But also it turns out that in this spin chain work, it is important that at least in some bases you have kink-like excitations, and we have the kinks, the topological excitations in the sine-Gordon model. So it can be an interesting direction to figure out whether anything similar can exist in a quantum field theory. And now a few words about the experiments. I think I have 4 more minutes, by the way. Roughly.
Yes, we have still 15 minutes.
Okay. So the experiments. So first, the brief overview or review of the experiments of the Vienna group. So what they have in the Vienna group is actually trapped rubidium atom gases. The way these gases are trapped, I mean, they use so different fields. There is a magnetic field which simply comes from electrical wires. Usually they use laser fields as well, and also some radio frequency fields. But the crucial thing is that the trapping potential is mostly due to the magnetic fields. So what they can do is that they can form, they can have a longitudinal potential, very shallow parabola, and of course a very steep transverse potential. Again, I would say a parabola. And if, as you may know, if the transverse potential is very steep, then the transverse modes are high energy modes, and they are not excited at low temperature. So your theory is essentially one-dimensional. But so inside the condensate, which is a quasi-condensate, a quasi-Bose-Einstein condensate, you can model the interaction, the short-range interaction of these rubidium atom gases as contact interaction. So at the end of the day, what you get is a Liebling-Niger model with an external trapping potential. You can have, of course, 2 of these condensates as well. And by suitably tuning the external fields, like the magnetic field, you can also have a situation in which you have 2 condensates. There is a potential barrier, but you can change this potential barrier, and this way you can introduce a tunneling term. And here you can see that there is one field operator from the other condensate and the other operator from the other one. So it's really a tunneling term. So this is still not sine-Gordon, but we are almost there, because sine-Gordon enters the game in the following way. If you only focus on the small density fluctuation of your bosonic field and your phase fluctuation, or in other words, you perform this Madelung-like transformation, then what you can do is that it's very easy to see that that if you introduce the relative coordinates for these variables, so for the phase and density fluctuation variables, then for the relative coordinates, you will get a sine-Gordon Hamiltonian, and this cosine term, cosine phi for the relative field, comes from this term. Of course, here the assumption is that you can keep rho 0, so the density of the condensate fixed. For the symmetric combination of your new variables, you will get a conventional Latinger liquid. So you have a Latinger liquid for the symmetric degrees of freedom, for the symmetric variables, and the sine-Gordon Hamiltonian for the relative coordinates. So this is how sine-Gordon emerges in these experiments. And the recent advances are the following. So what the devices that have been installed in the lab, and I had the privilege to actually see them, are these digital micromirror devices. If I want to simplify the story, what they do is essentially they shine light on the condensate. And what they can do by using these, they can have a very fine structure. So what they can do is they can manipulate this density, so the overall density, the total density of the condensates in a very accurate way. In particular, they can make it sure that this density is constant and it drops to 0 at the ends of the system, which corresponds to a box potential. So the parabolic trapping potential is not anymore necessary. They can really realize the box potential. And on the language of the sine-Gordon theory, it corresponds to actually Neumann boundary condition. But the claim of the experimentalists is that you can actually make this rho x, so the density of the condensate, an arbitrary space-dependent profile can be achieved. As far as I know, the main drawback of these DMDs is that inevitably they heat up your condensate, and I'm not sure how much the experimentalists managed to progress with this issue. But this is one disadvantage. So probably you cannot do anything what you want. And so this is very nice. I mean, this way you can have a spatially dependent coupling term here in front of the cosine, but this is not exactly what I was talking about. I was talking about adding external chemical potential, and it turns out that it's also doable. One way to do that is quite funny, actually. So basically, the alignment of these condensates is such that they are usually horizontally aligned. But what you can do is you can rotate them, and if they are vertically aligned, then the gravitational force of the Earth just introduces a chemical potential in the relative coordinates. So at least what you can do is a constant chemical potential, and actually there's also another method based on Raman laser beams, which is claimed to be able to do the same trick. So you can definitely realize constant chemical potential by which the experimentalists can inject solitons, and then their logic or philosophy is that once you inject a soliton or an anti-soliton, then using the DMDs, you can probably move them. So you can still, in a control way, more or less control way, you can initialize certain profiles and certain regions in which the solitons are condensed or accumulated, and regions where they are not. So this is the current in the state of the art of this experiment. When I visited the group, it was this year, I think March. And then I heard about all these advances, and I look forward to the papers they will come up with, and to see what exactly what they can realize and what impact or what physics they can see. But because I'm talking about inhomogeneous quenches in the sine-Gordon model, I think it is good to say that the experimentalists are now there so they are able to realize these inhomogeneous quenches by various ways. And finally, to finish my talk, I would like to mention one last application of this TCSA. I mean, we saw how it performed in inhomogeneous cases, but there is another problem which many of you are interested in, is force vacuum decay, and it turns out that these methods can be applied in force vacuum decay problems, at least in 1D. Namely, decay rates can be extracted. It is really non-trivial because you must have understood that in TCSA, you always have to be in finite volume. And if you're in finite volume, it always gives you a limitation to the maximum time you can perform your simulation, because at some point you will have boundary effects. So it is really a non-trivial thing to extract decay rates, but it has been done. It has been done in a 5⁴ model. And the method in that case was actually not a TCSA, it was another truncated space method. It was a bosonic, massive bosonic truncated space approach. Nevertheless, some ideas which were implemented are very similar to the idea which I said to you, I mean, namely not computing the matrices explicitly. And there were other works which focus on the Ising quantum field theory and certain perturbation of the tricritical Ising quantum field theory, again in force vacuum setups, where really this chirally factorized, so this upgraded TCSA was used. A common finding of this work is that the decay rate, there seems to be a mismatch in the decay rate with respect to the Coleman-Voloshin result, which is based on the instanton calculation and the thin wall approximation. I think it is probably correct, I mean, the mismatch, because very recently there has been a paper by the Heidelberg group, and their finding is it's a very different approach. It's not a numerical simulation actually, but they claim that these decay rates actually are time dependent, although mildly time dependent. So yes. So actually here what I wanted to demonstrate is that it seems that the TCSA can be applied for force vacuum decay problems as well, besides inhomogeneous quench problems. And with this, I have come to the end of my talk. I would like to say thank you for your attention, and I look forward to questions if you have any questions. Thank you.
Thank you, David. It was a really nice talk. Thank you.